Hi all, I'm Erin Carswell, Vice President of Exploration at Foran Mining, and I'm thrilled to be able to talk to you today about some of our exciting new exploration results. So these results build on our Tesla and Bridge Zone discoveries, along with one particular drill hole that gives us a taste of the growth potential to come. And hopefully seeing everything in 3D, as I'm about to show you, will give you an idea of the potential scale of these collective discoveries. And just a quick note, this presentation contains certain forward-looking information and forward-looking statements as defined under applicable securities laws. Please refer to the forward-looking disclaimer displayed on the screen and also available in the description of this video. First, just to orient you guys, Foran Mining, of course, holds a large claims package in Saskatchewan with our flagship McIlvenna Bay VHMS deposit located about an hour's drive from Flin Flon in Manitoba. And our geoscience and discovery team is active right across this package of claims. We have some great regional targets that we'd love to talk to you about at some point in the future, but today we're going to be zooming just to the Tesla area to the northwest of McIlvenna Bay. So here we are looking at plan view at the surface projections of McIlvenna Bay in red, the new Tesla discovery in yellow, and the even newer Bridge Zone discovery in orange. And the Bridge Zone here we're interpreting as a fold that links the two. So the results that we're releasing today relate mainly to the Northwestern End of Tesla. And also, of course, we have one additional bridge hole to talk about as well. Dropping beneath the surface now, and here you're looking at the drill traces for Mac Bay, the Bridge Zone and Tesla. And the colours that you can see on these are basically the mineralised zones coloured by copper equivalent in percent to keep things simple. And the holes included in today's press release are shown there in the teal colour along the hole trace. So McIlvenna Bay, you can see here, I'm going to highlight it in red. This is McIlvenna Bay here with the higher drilling density. It's around about 2 kilometres long and dips back off towards the northeast. You can see the Bridge Zone sitting here in the middle, and we'll show you a different view of that in a minute. We currently have three drilled holes into the Bridge Zone. And then, of course, we have Tesla, and that's this collection of drill holes here. I'm going to draw a big arrow here because we're nowhere near kind of understanding yet the extent of Tesla, how far it continues along strike. Currently, we have 15 holes into Tesla plus wedges, and we're looking at almost 900 metres strike length already. So again, when you put together the 2 kilometres of McIlvenna Bay, the Bridge Zone in between, another 900 metres at least at Tesla, probably more, we're starting to look at something really, really big as a mineralising system here. So yeah, really cool stuff. So what we're going to do now is look at these teal coloured holes, the ones provided in today's release, in a little bit more detail by drilling area. So starting with the Bridge Zone between Tesla and McIlvenna Bay, and we've followed up our first 2 mineralised holes with another great intersection, and I'll leave you to read that from the screen or as part of the release. But what's really interesting for me in the Bridge Zone is the structural complexity here. So we're talking about, yes, it's a little fold in between McIlvenna Bay and Tesla. There's also more structural kind of evidence that we see here in terms of faults coming through the area. And what these faults are doing is moving around mineralisation. So we do see some remobilisation in this area. And a good example of that is in this current hole from today's release, where we have a 13-metre shear zone that's running 1% copper. So we don't see that kind of thing necessarily everywhere else at Tesla and McIlvenna Bay. So this is quite interesting to us. It presents opportunity as well. It also presents a challenge in terms of understanding this area, but that's a focus for my team going forward over the next couple of years. We'll step out now to the northwestern end of Tesla, where we have 3 new wedge holes that we've released today. All of these wedge holes successfully intersected the target mineralisation. We've got some nice numbers shown here. And these were also really important as each hole intersected multiple levels of mineralisation, which provides us with additional evidence of the multiple ore lenses that we're seeing up the northwestern end of Tesla. And I think you might recall that the first hole where we saw these was in hole TS2310. We had an absolutely banging copper intersection in that hole. Also TS2312, the parent hole to 2 of these wedges, had some fantastic thick intersections of zinc and multiple levels of mineralisation. So what we're really interested in here is understanding the geometries of these lenses. You know, the Tesla main lens seems to be behaving pretty predictably and dipping off towards the northeast. What we wanted to understand was, is this a feeder zone? Is this a new structure coming in controlling these lower lenses? We don't see them everywhere else. And in that case, are we drilling at the right orientations to test them properly? So that leads me to our next hole, which is TS2314 wedge 2. And this is one of the last holes that we drilled this season. You can see it's coming in from a bit of an unusual angle. We typically don't drill from the footwall, given the dip of Tesla. But in this case, we wanted to. And the point was that if these lenses are dipping off towards the northeast and we can intersect one, we should get a nice thickened intersection as we drill down the dip of it. And that we did. So we ended up with nearly 50 metres running at over 9% zinc. So a really good intersection there. And while it's not true thickness, of course, because we're drilling down the dip of the deposit, or at least obliquely kind of across that plane, what it does mean is that it tells us something about the coherence and the continuity of the mineralisation in that down dip direction. So still a very important hole from that perspective as well. And then in terms of the orientation of the lenses themselves, I'm just going to draw on the diagram here, and you can probably already start to see it. But the lower lenses look like they're dipping very similarly to the Tesla main lens that I'm now highlighting in red, or at least sub-parallel. So that was an important finding for us in terms of the structural geology of this northwestern end of Tesla. But the most important hole from our perspective this year was one that we refer to as the Higgs hole. So this is hole HG2301. This hole was initially drilled to test a regional EM target to the north of Tesla, which was called the Higgs anomaly. But right now, what's relevant to Tesla is that as we were drilling this hole, we started to see similarities in the chemostratigraphy, in the marker beds, things that we were seeing that indicated that we were getting closer to actually intersecting the Tesla prospective horizon. And so we drilled on. We actually ended up drilling a fair bit deeper than we'd originally planned, but that paid off because we made this amazing intersection into the Tesla main lens, about 200 metres down dip and 120 metres along strike of the last known mineralisation at Tesla. So this is a huge step out. And the intersection was really solid as well. So we had an initial 4.5 metres grading 2.7% copper, 3% zinc and 0.7 grams gold, followed by a beautiful 24-metre intersection running over 5% zinc and over 0.5% copper. So very, very good result for us. What this tells us is that the mineralising system at Tesla is not getting any weaker down dip. And in fact, this is one of the better intersections that we've had into Tesla so far. So how does this intersection connect with the rest of Tesla? Well, we have a very well-constrained sequence of rocks in the hanging wall to Tesla that place this mineralisation bang on where we would expect the Tesla main lens. And you can probably, again, almost see it with the, just looking at this diagram, connecting the dots, but I'll draw it on anyway. So this is the 200-metre down dip extension that I'm talking about here from the main Tesla mineralisation down to the Higgs intersection here. And it's not just the down dip potential either. So we also did a borehole EM survey on this hole, and we got right down to the bottom here and saw that the mineralisation does seem to extend along strike in both directions as well, as far as the technology can see. So we're nowhere near close to closing out this mineralised zone at Tesla. And in fact, it's led us to rethink our winter program and the kind of scale that we were planning for there. So we'll zoom back out now to the plan view, and you can see there the original shape around Tesla that we had. And I'm just going to grab a yellow here. What the Higgs hole means for us is that the strike is extended to the northwest further than we expected, and the dip is extended back down in this direction further than expected. And so, of course, what we're wondering now is how far does this go along strike? This down dip extension of the mineralisation. And so we've planned a program now with 7 drill rigs on the ice starting in January 2024 to test this idea. We want to know how big could Tesla be. So this is our rough drill plan. You can see there are big step outs here going down dip, going along strike. And I'm not necessarily even saying that we're going to find the edges of the ore body like this. I don't think we will. But we may get more of a feeling for where the centre of gravity of Tesla is and just how big it could be. So this is a really important program for my team, really exciting results for us this year that we're hoping to follow up. So wish us luck, and we really look forward to bringing you some more results of the winter program as well. Thanks for listening. Cheers.